Hi everyone, my name is Walter. I am a senior data scientist at Neuralmed. We are okay. We are a Brazilian health tech company that starts with analyzing X-rays and some image exams like tomography and ultrasound. And the main goal of this talk is a little more about the NLP uh, works that we are doing here on the last few 2 years, maybe. Um, in the other side of the company, not only analyze X-ray exams and tomography and ultrasound, we are too analyzing the medical record, medical reports, and everything that is unstructured data that is mostly information about the patients that go to hospital, clinics, and some insurance plans. And that whole information given to us a little timeline about the patient. So we need to extract the information and put that in numbers and time and look and maybe geospatial data, and we can now track the patient and how this pathology or maybe some diseases are spreading. However, the medical report is considered a free text form, but not exactly a free text form. What happens in Brazil that our company is working is that medical reports here change a little bit from hospital to clinics and everything like that because each clinic assumes a little bit a default medical report. This default medical report is like when the case the patient doesn't have any pathology, doesn't have any disease. So each sentence of that document says like, okay, so the stomach is all right, the stomach doesn't have any problem, the bladder doesn't have any nodule or mass, and everything like is perfectly normal. And what happens is that the suggestion for the doctors and nurses is that they make a little change in each sentence or each part of the text, and it may be just this little change is modified by the default medical report for that specific hospital. So each hospital or clinic have this little default, and here I can show you an example in Portuguese. I will translate. So there is abdominal medical report. They start to the title is about the type of exam, so it's a tomography in the region of abdomen and pelvis, following by the possible hypothesis, clinical hypothesis. So there is a fever, and maybe this fever is associated with some stomach disease. And after that, they start to make this little information about everything like normal, the bilis is normal, everything is normal, kidney is normal, and they start to talk about, okay, so there is a little splenic disorder, so it's not a little not so normal in the region, and then is a pancreatitis, a bladder disease, and they change only the sentences that is associated with that region. So the main idea is to make classifier for the abdomen region. Why is that? Because this abdomen region is the region in the body with the most extensive number of organs. So everything that happens on that region is associated with some disease that can be spread for the other parts of the body. So we have something that you can eat or maybe drink, and you can have problems with the stomach, kidney, uh, pelvis, and everything that happens there in some way gets a follow to another part, like the brain, lungs, maybe the the arms, everything like that. So it's very relevant to know how to classify the region to make the patient more to leave the patients more quickly to a treatment. So we can make the he take medicine or maybe making more exams faster than the disease can spread in his body. For that, we select with a few doctors, maybe some labels of the pathologies more interesting to our clients, hospitals, clinics. And that was more mostly like nodal mass that's associated with cancer, problems with fluid collection between the organs, perforation that can happen when you have some accident, like a crash, for example. Problems with spine bone, you have a little crash, like I said, with the perforation, but in your in your spine. So there is a problem there. For this analysis, what I was doing was selecting medical reports for 10 to 12 plus years of images exams, and it always will give me almost like 400,000 medical reports. And when you think about these documents by unique sentences that can change and maybe they give you that pathology information, is around 76,000 uh, unique sentences for X-ray, tomography, and ultrasound exams. So the problem here is that not every class is balanced with the whole data set. So you have the northern mass that's more relevant because we have several problems like cancer or maybe a little increase in region in the stomach and intestines. So, and when we compare with the problems, cyst that's very small compared with another mass, this is very large compared the problem in other mass, and so we have a more extensive data set for that problem. So the problem of my data set is that relative unbalanced. And when we look for the 76 unique sentences, 1,000 sentences, we have this little 20,000 of sentence that doesn't relate to any pathology. They give us the normal situation of the patient, and most of the combination of these other diseases, like you have a kidney problem associated with stomach problems, or maybe you have a colon and a problem associated with some cancer. This little combination here, when we code that, we see that they already are unbalanced. So it's not exactly the same but the question is how well this is can merge one label to another. And when we're looking for intersection between these labels, we see that some classes are more related to another, like trauma. Trauma, as I say, there is a car crash, you have a fluid collection. So some water, blood, maybe other type of fluid can be inside and between the organs. So there is a 24% uh, intersection of similar sentences between these two labels. And we're looking for the perforation, they have 77% with pain pneumonia peritoneum. Sorry about the pronunciation of this label, because it's like you have this perforation of the abdominal region that put air in the lungs that doesn't need to be exactly on that region. So some classes are more likely to happen to another one. So we need to know which the classes have few examples to increase the data set and make a better model. For starter, we create a baseline classifier. We're using a BERT neural network because we're training a BERT language model with your 10 plus years data set from image exams. These exams are generated by the São Paulo Image Data Center. The baseline model gives a F1 score and recall above 70%. However, the doctors and clients, they want a model in production with better results, like 92% or above that. So there is a problem here with the data set that we have and the model that we can create it for the what the doctors, clients, or hospitals, clinics, etc. wants to have. So the data is unbalanced, and we need to think about how to make that more better. Like, okay, so maybe decrease the number of samples from the large labels, or maybe giving some data augmentation. But the problem is how to make that a smart way to select which sentence we need to apply the data augmentation. That's the main goal of this project, like a smart way that we can increase the data set, doesn't have the problem with overfitting the classes with more data set and give better results. When we think about the baseline classifier again, what we see is that there are several classes between the 70% and 92 thresholds, and we verify that these labels, if we recall below 90%, having more than 70% of the keywords from all the labels. So what we define as keywords, I the keywords identify as a non-chunk token. So a non-token that is the head of the sentences. So we have this sentence that was talking about organ or a body location or some symptom of the disease. That is basically a noun. It's a root of the linguistic analysis of the whole sentence. So every token is associated with this token, this primary token. And when we think about this keyword that happened that's and connect with that intersection between labels, we see that some classes with 92% more better recall or F1 score have this condition that the labels with recall between 80 and 90 have difficulty when tracking this pattern because they don't have this 70% of the keywords found in, they have this 70% of keywords found in another labels. When we think these keywords, for example, for nodal mass, we have this specific formation or maybe mass, nodally, the exam, like increasing in the injury of the region, these little words that, again, are related to organ, to body part location, or maybe the symptom, are exactly giving us the frequency of this idea, this main idea of the sentence. And when we put that in the table, when we compare the non-chunk root words with the frequency and the associated class that this non-chunk token appears, and precision recall FA score of the baseline model, we can compare the distribution for each group. Like the first group is what the doctors are waiting, so we get the labels from that have the recall better than 92%, and we compare it with the labels we have the recall worse than 92%. What we see is that it's not so discrepant, but they have some problems in some regions of this distribution. Here we have the whole frequency distribution of the non-chunk keywords in the dataset. Here we have the keyword frequency for recall above 92% and below. So when Because the histogram of keywords frequency and the amount of size or the frequency have, we change that for compare with the cumulative distribution function. And what we see is that they are little bit close one with another, but when we apply the homomorphism test or maybe some other comparative methodologies for define if a distribution is originated from both distributions are originated from the same distribution, we see that they don't support the idea because the recall above 92% start to increase after point after 15% they start to increasing and the distribution start to have this discrepancy. And below that, on the region between 5% and 15%, these little variations have a little gap between both of these keywords. So the idea is start to think like, okay, so the distribution of the frequencies of the non-chunk words are very similar, but not exactly the same. We don't the tests with the similar distribution doesn't give us a value that say, okay, they are both from the same distribution, but can't be possible. It is not exactly equal. So if we change a little bit, we start to increase a little bit to make this the, the worst distribution, which we call below 90%, start to make similar, looking similar in these regions and after that. So between zero point 0.5 to 0.40 or maybe 0.35%. So the idea to increase it only a little bit works very well. We start to make a step function to have this increasing and to not uh, make a overfitting of the using data augmentation. We start only for a few samples. So a curve was between 0% and 0.15% can increase 3 times. So we get the sentencing, we apply our transformer language model specialized in Brazilian Portuguese using a contextual word embedding. So we change the token next to the non-chunk word without losing the context or include one token on the sentence before or after this non-chunking. And we increase the dataset with that. This gives to us a increase of 250% from the original dataset. And you can say, it looks more similar with the beginning histogram of the labels at the beginning, but what changes is that the top five are the classes with more data set that is related to other labels. So we cut the top five classes and we start to selecting sample to complete your original data set by the class with the lowest number of augmented dataset generated by this methodology. Supplement your training data and supplement your validation data. So our model improved almost every class. We got our FAU score like around 96%, and our class start to have a FAU score above 92%. We start to make questions about, wow, maybe we overfitted the data. So we get 18,000 unlabeled medical reports from our clients, and we select a group of doctors to validate these results. They took a few months to validate that. And we start to apply some sharp values or Lime interpretability to show where exactly the model are looking. and the doctors validate the results above 93%. Was great because we applied that to production, I think, in June last year, and they are running to our clients since that with very great results in production. Um, the next problem was how to correlate that or how to know which non-chunk token is exactly a body location, a organ, or maybe a symptom. So we can try to address this problem, developing last year, by the end of the last year, name entity recognition model that we combined with your gastroabdominal model from uh, based in batch transformers. And these two increase the complexity how to stratify the data and how to sample, but this giving our better results too. But that is for future talk, so we can talk more that in the Q&A after finishing this time. So just for finishing, NLP team changed a little bit from last year. We still have the Jessica tech leader. Now Capella is our manager. I'm the as a data scientist, Tainara as data scientist, and we have now a junior data scientist that is Luana. She started with us in January, and our medical team is André Castilha and Guilherme Crespo. There is the CTO, André Castilha, and Guilherme Crespo is also associate medical doctor for uh, try to talk with the clients with more increase the ideas or in production or maybe the problems we can solve for directly in the hospitals. So thank you very much for this time, and I see you guys. I'm hoping to take questions on the next on the Q&A, and see you.
What an excellent presentation to end this conference day. A huge thank you to all the speakers for their insightful talks covering state-of-the-art NLP and LLM research and best practices for healthcare and life science. Today, we learned about the significance of amalgamating structured and unstructured data to create comprehensive longitudinal patient stories, the transformative potential of AI in advancing precision oncology, the challenges in sourcing diverse and high-quality data for responsible AI applications. Additionally, we shared insights on using large language models to enhance model accuracy and also to optimize and predict inpatient violence and delirium using NLP in an acute care setting. Another big thank you goes to all of you for joining this community, this conference yesterday and today, and for contributing with your questions and ideas and your own experience. We do this conference for you. If you would like to watch any of the sessions again or watch those that you have missed, you can come back and watch them right here in the replay sections here on the conference platform on demand. The sessions will be accessible for the next 2 weeks. Also, please let us know how you like the event so that we can make an even better one for you next year. We have shared the link to the feedback form right here in the chat. Thank you. For all those who would like to dive deeper into applied NLP, we'll be back in the following week with 5 days of virtual live NLP and LLM training courses and certification. These 5 days of workshops will walk you through state-of-the-art LLM and NLP using Johnson Labs open source library, healthcare-specific library, and visual document understanding library. Check out the link in the chat to see details and to register. Once more, thanks again to all of you. I'm very proud of this amazing community. Please do keep in touch with me, with the other people here, with the Johnson Labs team, and have a wonderful rest of your week.